Special cases of linear equations. In the previous tutorial, we explained how to solve a system of linear equations. Recalling what we said in tutorial 9.7, it is clear that we can identify three methods for solving such systems. 1. Elimination method, in which one of both equations is multiplied by suitable coefficients, so that one of the variables can be eliminated after adding each other the equations of the new system obtained after such multiplication. 2. Substitution method, in which we choose one equation to isolate a variable and substitute the equivalent expression in the other equation, to express it entirely in terms of the other variable. And 3. Graphing method, in which we plot the graphs of both linear equations and see where they intercept, as the coordinates of that point represent the solution set of the system. However, all examples discussed in tutorial 9.7 were carefully chosen to give a single pair of coordinates as a solution set. Such systems of linear equations that give a specific number pair as solutions are called independent systems of linear equations. Moreover, all values found for the variables in the previous tutorial were integers. It is clear that such examples represent only a small portion of all possible systems containing linear equations. In the next part, we are going to explore some special types of linear equations that require attention. 1. Linear equations with no solution. Let's take a look again at the first system of linear equations provided in the introduction section of this tutorial. We have the following shown on screen. If we use the elimination method to solve it, then the first equation must be multiplied by -2. This yields, we have the following shown on screen. Adding both equations yields, we have the following shown on screen. This new equation has no solution, as no number multiplied by 0 gives a non-zero number. Therefore, the original system of equations has no solutions. If we try the substitution method instead, for example express y in terms of x in the first equation and substitute it in the second equation, this yields, we have the following shown on screen. We have the following shown on screen. This too is an equation with no solution, as no number can multiply by 0 and give 1. Last, let's try to solve this system graphically. Thus, for the first equation, we take x equals 0 and x equals 3. The corresponding y values are y equals 3 and y equals 0. Therefore, the points A, 0, 3, and B, 3, 0, belong to the graph of the first equation, so they are used to plot it. On the other hand, if we take x equals 0 and x equals 3.5 in the second equation, the corresponding y values are y equals 3.5 and y equals 0. Therefore, point C, 0, 3.5, and B, 3.5, 0, belong to the graph of the second equation, so they are used to plot it. This is the figure obtained by plotting the two following graphs in the same coordinate system. We have the following shown on screen. As you see, the two graphs are parallel. It is understandable as the system of equations had no solutions, therefore the lines that represent each equation must have no common points. In this way, we obtain an important conclusion about the systems of linear equations. If a system of linear equations has no solution, the graphs that represent each equation are parallel, i.e. they do not have any common point. The systems of equations that have no solution are called inconsistent. 2. Linear equations with an infinity of solutions. Now, let's consider the other system of linear equations we gave in the introduction section, i.e. we have the following shown on screen. Let's try to solve it through the elimination method. Thus, multiplying the first equation by -2 yields, we have the following shown on screen. Now, let's add the two equations to eliminate any variables. Thus, we have the following shown on screen. Since this equation is true for any value of x and y, we say this system of linear equations has an infinite number of solutions. Practically all numbers that give a true result for the first equation are solutions for the second equation as well. Therefore, since all solutions of the first equation are also true for the second one, it is obvious that we are dealing with equations that have the same graph. Such a system of equations is called dependent, as well as the equations contained in it. The figure shows the graph of the two linear equations of the last system. We have the following shown on screen. Example. Determine whether the following systems of linear equations are independent, inconsistent, or dependent. We have the following as shown on screen. Solution. A. Let's use the elimination method to solve this system. Multiplying the first equation by 2 yields, we have the following shown on screen. Adding both equations to each other yields, we have the following shown on screen. This is an inconsistent system of linear equations, as it has no solutions. This is because no numbers multiplied by 0 can give 11. B. Again, we can use the elimination method for convenience. Thus, multiplying the first equation by 2 yields, we have the following shown on screen. Adding both equations to each other yields, we have the following shown on screen. This is an independent system of linear equations, as whatever value we insert for x and y, the result will always be 0. See, now, let's use the substitution method. We have the following shown on screen. Thus, we have the following shown on screen. Therefore, this is a dependent system of linear equation, as it has only a number pair as solutions that correspond to the point 7, 2 in the graph. That is all for lesson 9.8.1. To continue this tutorial, please watch 9.8.2, Systems of Equations with one linear and one quadratic equation. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.